Yep. All right, guys. Questions on the homework? Questions on the homework problems? What we're talking about today is rational exponents. Rational exponents. So we have two main properties here. One, a to the m over n is equal to, or is the same as a to the 1 over n to the m. And the reason we can do this is powers of powers multiply. So 1 over n times m is the same as m over n. Or we can go backwards, we can split those apart. And as we had yesterday, the nth root of a is the same as a to the 1 over n. Or we can also say that a to the 1 over n is the same as the nth root of a. Now the reason this is helpful is that if we're trying to take and simplify these fractional exponents without a calculator, it gives us a little bit easier way to work this out and to solve these. Now the same thing is true for our a to the negative m over n. To make an exponent positive, we move it from the top of the fraction to the bottom, and we do our same property here. Now, seeing this in a definition, we can kind of get it, we can kind of see it, but I think it is a little bit easier if we actually see and apply this to something we're simplifying. So if we look at the first one here, 16 to the 3 halves, and the whole goal is to be able to do this with, for the most part, without a calculator. We can rewrite this because a to the m over n is the same as a to the 1 over n to the m. And for us here, we could rewrite this as 16 to the 1/2 to the 3rd. Now 16 to the 1/2, if we rewrote this back as a radical, let's change pen. Really what we're saying is the square root of 2, n is 2, so we could put that 2 there, but it's understood as a square root. Square roots, that index is 2. We can have it there, we don't necessarily need it. Questions on this so far? Questions on how we got to this point? Because just trying to go from 16 to the 3 halves or 16 to the 1/2, it might be hard for us to see what that is. But really, 16 to the 1/2 is the same as saying the square root of 16. What times itself is 16? 4. So being able to rewrite it from 16 to the 3 halves to the square root of 16 cubed, well, we can take square root of 16, that's 4. Now 4 cubed is 4 squared is 16. So to cube it, we just have to multiply by 4 one more time. 4 carry the 2. 4 times 1 is 4 plus 2 is 64. Yeah. So this gives us a way that taking 16 to the 3 halves, where we just couldn't jump to the answer, it gives us a way to break it down and actually solve it piece by piece. And luckily for all the ones that we're doing here, I mean 16 to the 3 halves is 64. Now, not every problem we're going to encounter is going to work out that nicely where we can just type it in and get an answer. Questions on A before we look at B? 32 to the negative 3/5. Well, first thing we need to do is make that exponent positive. So to make an exponent positive, we can move it from the top of the fraction to the bottom. Now at this point here, it's going to get the same treatment that what we just did. Because we can rewrite our 32 to the 3/5 as 32 to the 1/5 to the 3rd. And 32 to the 1/5 is the same as saying we want to take the 5th root of 32. Now, kind of keeping in the same form, we need to figure out what times itself. 5 times is 32. It is 2. Otherwise, I didn't finish writing this out. Now we can factor tree this. So with factor trees, we want to rewrite it as primes. Now the smallest prime factor of 32 is 2, and that's 2 times 16. Well, 16 is 2 times 8. 8 is 2 times, and 4 is. So our prime factors are 1, 2, 3, 4. 5 is the same as 2 to the 5th. It gives us a way to see what times itself and take the radical of it, because 2 to the 5th is 32. So all that's telling us is that the 5th root of 32 is indeed 2. Now what do we have left? 1 over 2 cubed. 1 over 8. 2 to the 3rd is 8. Questions on this here? Any questions on problems A or B before we look at problems A or B? All right. Next one we have is 64 to the 4/3. Well, we could say this is the same as 64 to the 1/3 to the 4th. All right. 64 to the 1/3 is the same as the cubed root of 64. So we need to find a number times itself 3 times, that is 64. 4. 8 would be the square root. 8 times 8 is 64. Now 4 to the 4th. Well, we know what 4 to the 3rd is. 4 to the 3rd is 64. So to get to the 4th, we'd have to multiply it by 4 one more time. Our 4 times 4 is 16. So 6 carry the 1. 4 times 6 is 24, plus 1 is 25. So 4 to the 4th is 256, telling us that 64 to the 4/3 is 256. (16 to the negative 5/4). 1 over 16 to the 5/4. Same as 1 over 16 to the 1/4 to the 5th. (1/4), 16 to the 1/4 of the 4th root of 16. We're looking for what number times itself? 4 times is 16. 2. Which now tells us we have to take 2 to the 5th. Well, what is 2 to the 4th power? 16. We just had that, yes? So we need to multiply by 2 one more time. 16 times 2 is 32. That's it. And that's the nice thing about this property is it gives us a way, especially when these numbers are nice enough to work, to solve these here. Not every number is going to work out this nicely. Because if, like the last one here, if it was 18 instead of 16, we can't do this because we can't take the fourth root of 18. It just does not exist. Solving equations using nth roots. We've done this before, but we called it the square root method. It still works the same. We have three main steps. First, we need to get the term to a power by itself. Now, the main cases this works is either one, we just have a variable to a power, like this here, or the only variable that shows up in the equation is inside of a set of parentheses that is also to a power. So one, we got to get the term to a power by itself. So here, it's telling us that 4 times x to the 5th is 128. Is our term to our power, our x to the 5th, by itself? No. What is with it? So we need to divide both sides by 4. 4 over 4 simplifies to 1, leaving us with x to the 5th is equal to 32. Now is our term to a power by itself. Step number 2. Take the nth root of both sides. Now, what would our nth root be? We take the 5th root, because our 5th root in 5th power with x would simplify to x. Now the question is, did we take an even root or an odd root? Odd. So there's one real root. Now with this here, with these here, we can grab the calculator and see the 5th root of 32 is 2. So x is equal to 2. And that's it. Now, according to the fundamental theorem of algebra, the number of solutions should equal the degree, and any repeated solution should be counted equal to the number of times that it's repeated. So since the degree here is 5, we should have how many solutions? 5. But as we said yesterday, since the degree is odd, we should have one real solution. The other 4 are complex. And what did it ask us to find? We found the one real solution. The one real solution is 2. The other 4 are complex. It didn't ask us to find all solutions. It just asked us to find the real solutions. We're done. Questions on this here? So the other solutions for this here are going to be our I terms, our terms with I. So this one. Yep. Let's take the batteries out of this calculator. So, algebra solve 4x to the 5th minus 128 equals 0, comma x. Zeros. Yeah, there are other solutions. I can't remember how to turn this thing into mode. What's the thing? Real polar. Yeah. Yeah, because there are ways to get it. I'll figure it out in a minute. Yeah.
So I know we have the square root with it's like I squared and everything. Would I make that together?
Do we have a middle term? So similar to this here, yes? Did we have another term besides the variable? Because we only have this variable, so we could use this method. If I have a middle term, I have another x. So if we had, say, x to the third, I can't do this. I have to get it equal to 0 and solve. Yep. If you're stuck on that one, move to the next one. All right. X minus 3 to the fourth equals 21. Is our term to a power by itself. What's our term to a power? X minus 3. Do we have a number being multiplied in front? No. Do we have a number being added to it? So it is our term to a power by itself. Yeah. So we can take the nth root of both sides, and our root in this case would be 4. Because here the root and power would cancel, leaving us with x minus 3. Now, did we take an even root or an odd root? Even. So we have how many solutions? Because if we take an even root, we have 2 real solutions. So let's see what the fourth root of 21 is. Or, if it doesn't give us a nice number, let's leave it. Because there is no fourth root of 21, we could try factor treeing. Well, the first prime number that goes into 21 is 3 and 7. We can't take the fourth root of 3. We can't take the fourth root of 7. So it's just the fourth root of 21. That is as simplified as it gets. Last step is to solve. So x equals 3 plus or minus the fourth root of 21. We'd want to put the 3 in front because of the plus or minus. Because really what we're saying is that we have 3 plus the fourth root of 21 and 3 minus the fourth root of 21. And it's more based off of number theory than anything else why we'd put it first. Yeah, because if we had subtracted 3, negative 3, plus or minus that root. Because we want to put that number we add or subtract in front of it. Saying that we're adding the fourth root of 21 to it and subtracting the fourth root of 21 from it. We're adding and subtracting it from that term. Does that make sense? Questions on this here? 5x to the third equals 320. We need to divide by 5. These will cancel, telling us x to the third is equal to is the term to the power by itself. Yeah, the only thing we have left is x cubed, yes? So we can cube root, because our cube root and third power would cancel, telling us x is equal to 4. So this here would be our only real solution of this here. And it is possible to get the other solutions from here, and that's kind of what I was doing earlier, is we can actually use synthetic division to get the quadratic and then solve a quadratic to find the complex solutions to this here, but x is equal to 4. I need to fix this one, or I need to fix your note sheets, one of the two.
It's just yours.
It's just mine. It says +4. Mine had +3 originally. I think the reason that it changed was when I copied it on that sheet, I put a 4 instead of a 3. So is this by itself?
Yes.
Yeah. We can take the 4 through to both sides. These would. X plus 4 is equal to plus or minus to the 4 through to 24. Now, I'm going to do the factor tree again because it's 2 times 12. 12 is 2 times 6. 6 is 2 times 3. So this would be 2 to the third times 3. I can't take the 4th root of 2 to the third. Because for us to take a 4th root, how many 2's do I need? I don't have enough 2's. There is nothing that simplifies. If it's not the case, but say this was taking a cubed root, we're looking at the cubed root of 24. Well, we could take the cubed root of 2 to the third. That would be 2 cubed roots of 3. That would simplify because I do have enough 3's to take a cubed root of it. I don't have enough 3 or 2's to take a 4th root. Does that make sense? This is some of what we are going to encounter later where, yes, we can reduce that radical, but the calculator won't do it. Neither calculator will just give us that root, unfortunately. Minus 4 minus x is equal to negative 4 plus or minus 4th root of 24. Questions? Do we feel comfortable with these here? All right. I'm going to skip to 15. Last problem before well, it is the last problem. X plus 5 to the 4th power. Is the term to a power by itself? Yeah. So we can take the what? Well, yeah, kind of. 4th root. Because the 4th root and 4th power would cancel, telling us that x plus 5, 4th root of 16, 2. And because we took an even root, we would put the plus and minus, as we've done up to this point. Now we can solve for x by minusing 5, telling us x is equal to 5 plus or minus 2. And all the problems we've done up to this point, we've said this is the end, yes? Can I take negative 5 plus 2? Yeah. I can actually figure out that negative 5 plus 2, well, that is negative 3. And negative 5 minus 2 is negative 7. We can actually add and subtract, because if we can add and subtract without having to get the decimal approximation of that radical, we need to add and subtract. If we can simplify it, we need to simplify it. Because up to this point with the plus and minus, we've been left with that 4th root of 24, that 4th root, that radical, which unless we turn it into a decimal, we can't add and subtract. Here, we can. So we're going to. Questions on this here? That's it? 16? This one? Okay. So actually, yeah, we can look at 16. Is, well, our terms by itself, yes? So here, these would cancel, yes? Now, are we taking an even or odd root? Odd root, so there is one real root. Because with odd roots, because if it's an odd root and we have a less than 0, we have one real root. If a is equal to 0, we have one real root, and when a is greater than 0, we have, well, one real root. This is odd, so we do have, because when n is odd, we either have one real root, or one real root. Now, I have a feeling there is no cubed root of, or at least that's not a nice number. But it is possible to cube it and get back to negative 14. We can take the odd root of a negative number. Now, there's two ways to write this. One is we can take that negative and move it to the front, move it outside. The other option, don't know why I wanted to write 3, is to leave it inside the radical. I will take either one. And I'll show you why that works here in a second. Last thing we have to do is get x by itself. So we can say x is equal to 2 minus the cubed root of 14 when we take that x out front. If we left it inside, we'd have 2 plus the cubed root of negative 14 because the negative is inside that radical. Okay? Now, specifically, I'm going to look at the cubed root of negative 14. Well, negative 14, are we comfortable with saying that's the same as negative 1 times 14? Yeah, because negative 14 is just negative 1 times 14. Well, according to our properties of radicals, two radicals multiplied with the same index, I can split them apart into two separate radicals. Because when they multiply together, we get the numbers inside. Now, the cubed root of negative 1. We've already seen the cubed root of 14. It's not going to work. Cubed root of negative 1 is, lo and behold, negative 1. So that means for us here, we'll have negative 1 times the cubed root of 14, or just negative. That's why that negative can come out, because it's just, really, we're taking the cubed root of negative 1, which is negative 1. Does that make sense? And this is also why we can't take an even root of a negative, is because there's no way to multiply 1 by itself and somehow get a negative number. But that's it. Yes.
So, really, right there.
Mm-hmm.
Right there.
Yep.
But how did you get 2,401? Oh, okay. Never mind. That was a joke.
Do that there. I'm going to put it right here. This is a very big worksheet for 12 problems. There is a back, by the way. Yes. There's nothing worse than turning the paper in and finding out there's a back to it.